Damn it. Let's see here. So, um, this was the board from maybe this hour on whatever day, Friday, right? We talked about different ways of storing pain, different strains of pain, okay? Modes of pain storage. And we developed a mathematical process for figuring out exactly how much pain was stored in a stretched spring. We did that by getting two carts to move at the same speed. The carts had the same mass, they had the same speed. That was our way of verifying that they had this equal amounts of pain stored in their motion. To make that happen, we had to stretch the springs so that the area bounded by their graph of force versus stretch were equal, okay? And so that yielded the equation 1/2 K, the spring constant, times the stretch squared, which has the units of Newton meters, okay? Not newtons per meter, but Newton meters. Then we had all these other modes of pain storage. And so what I had for you to pick up over there was this thing, injury transfer model cheat sheet, okay? Injury definition, for right now, you just need to think of injury as pain, okay? And pain is measured in Newton meters, aka kilogram meters squared per second squared. So dimensionally, that's what's happening, okay? We've talked about several different modes. And come on, battery. So we got E. That is elastic. When are we fearful of the potential for being hurt by by elastic injury? I almost slipped there. Springs and rubber bands, particularly when they are stretched. Springs and rubber bands stretched. Okay? Equation E sub E equals 1/2 K delta X squared. Okay? Evidence that the injury has been transferred, that the injury has gone into a different form. The spring is, okay, there we go. Stretched less stretch. What were some other modes? So, the other one that you have an equation for, E naught. You know what? I'm going to change less. I'm going to change that to, because it could be, this says evidence of injury transfer. It could be transferred in, it could be transferred out. So I'm going to change this to change in length. All right. E naught, that is called rest injury. When is that type of injury present? When mass. Okay, so it turns out that mass is just another mode of injury storage. Okay, so this is the injury, the potential for injury you have just by the state of being. Okay, and that is E naught equals MC squared. Something about the Taylor series or something is involved in that. I have vague recollections of a great deal of pain in some physics class a long time ago. Evidence of injury transfer, that would be a change in mass. And then some of the other ones that we're going to need, we talked about these a little bit last time. EG is gravitational. Why am I making that box so small? That's dumb. Gravitational interaction. When is that present? That's when things can fall, right? That's when there's a potential for gravitational injury. Equation EG equals TBD. Evidence of injury transfer. Change in height. EK, that's kinetic or motion. Now, interesting thing about that, motion is relative. So this thing's kind of like relative, okay? Because there are frames of reference where things are at rest relative to each other, and in those frames, they would have very minimal potential for injuring each other due to their motion, okay? There are other frames of reference where things have a high rate of speed, and there would be the potential for great injury there. So when things move relative to each other. That's like what was the big news with SpaceX the other day? They launched a Crew Dragon. How fast was that thing going when it docked with the International Space Station? Like, we worked it out. It's like 17,000 miles an hour, okay? But it didn't destroy the International Space Station. Why? Because the International Space Station is also going about 17,000 miles an hour. They're both going very fast, but relative to each other, not so much. So when they dock, it's not catastrophic. Okay, so when things move relative to each other, equation is going to be EK something. EK equals meh. Evidence of injury transfer. Change in speed. All right. EG, EK, E naught, EE. Ooh. Smell that. Smells like ashes, okay? Because burning. But Jake, hold those. How did it feel? Not hot. How did the not hot balls burn the paper? Yeah, exactly. What happened? They smashed. So they're moving. When they smash, what happens to their motion? Yeah, they're not moving. So that's a change in motion or a change in speed. That's a sign of injury transfer. Where did it go? Ooh, burnt the paper. Okay. So we call that category etherm. So I'm going to call that ETH, or like a broader category would be EDIS for dissipative. And under the umbrella of dissipative is, oh gosh, heat. I shouldn't use that word there, but I'm going to. Heat or sound or vibration. This is where I have to rely on your other teachers a little bit. What do those things all have in common at the molecular level? Motion, increase in motion, right? So if we're increasing the dissipative injury, that would be like an increase in vibration on an atomic or molecular level. Sound is the vibration of the air. Okay, vibration is the vibration of vibration. When is this injury present? Great question. When things burn, or what's another sign of thermal injury? Fans of exothermic and endothermic reactions? Okay, what's that? Melting is a change of state. Okay, I guess I should throw that over here, right? Change of state or change of temperature. Okay, that would be E dis meh. It's kind of unnecessary. It's just like our thing that we have out there. EDIS, and we'll talk about this varyingly here. It's really straightforward. It's real easy to get injury stored thermally. Okay, like if I take this expensive frictionless cart, but I'm a numpty about it, and I give it a push. Frictionless. Okay, like it's upside down, so it slows down pretty quickly. It had some motion, now it doesn't. The table's warmer. Hey kids, come back next year. I'm going to make the ISCCSD Foundation buy some thermal imaging cameras. Ooh, that'd be exciting. So it's easy to take injury that was motion and store it thermally. It's much more difficult to take injury that's stored thermally and get it into motion. Okay, we're going to talk a little bit about the conservation of injury, which the guided studies here at West High called the conversation of injury. Up until like 5 years ago, that one took a long time to get changed for some reason, but we're going to have a conversation about the conservation of injury. It wouldn't violate conservation of injury for that thing to start moving and all of a sudden have some injury stored in its motion, provided the room got colder. Like, can you imagine how weird that would be if like the room just suddenly got really frosty and the chairs started to like slide around? It wouldn't violate conservation of energy. Okay, it would violate some other things, the laws of thermodynamics, which we'll discuss a little bit later. But that's kind of the weird thing about thermal or dissipative forms. I consider it to be like the Carlos O'Kelly gift card of injury storage. Anybody here have a Carlos O'Kelly's gift card in their pocket? You're always going to have it in your pocket, right? Like, it's real easy to put money into that. Like, Jesus, I don't know. What are we going to get them? Oh, there's Carlos O'Kelly's. It's just not going to be a gift card, right? Boom, real easy. That money goes into the gift card. Then you give it to the person. They're like, why do I want diarrhea? Okay. So, you put in like, I don't know, $100 or whatever, and like, they're going to get like chips and salsa, but they're never going to get all that money back out, right? So it just stays in there. That's how dissipative injury works, okay? Injury goes into that form, but you never get it all back out, okay? And again, that ties into the laws of thermodynamics. We'll get there eventually. E naught, Eg, Ek, Ethermi dis. As we need other forms, we can add them to this chart, although apparently as we need other forms, we can add it to this chart because we're at the bottom. What I want us to gain some comfort with today is a representational scheme that your book uses. It's awesome. I've never seen a textbook do this before, but your book's cool, man. As far as books go, it's a terrible book, but it's the best book I could find. This is called LOLz, LOL diagrams, okay? And so we're going to head over there and start to put this together. So let's slide over there. LOLz, all right? Injury model worksheet 1, qualitative injury storage and conservation, LOLz. All right, so why are these called LOLz? Why is this pin not working? Why are these called LOLz? Let me show you here. Because you're going to do this. LOL. Inside the O, that's your system. So what goes in there? Well, we read the problem here. In this situation, shown below, a spring launches a roller coaster cart from rest on a frictionless track into a vertical loop. So I've already kind of highlighted the words that are really important, implicit suggestions in this problem. Assume that the system consists of the cart, the earth, the track, and the spring. Okay? And then, gosh, there's reference to a spring here. That suggests what type of injury might be potentially involved here. Elastic. So I'm going to have E. All right? I see mention of it being from rest, which kind of implies that it's not always at rest. So that means we might be dealing with EK. And then I see something about a vertical loop. Vertical implies a change in height. So I'm going to have EG. I don't see any mention about friction. In fact, I see it's frictionless. So I'm not going to include that. Okay. I'm going to put those same forms on the second L and anchor them to specific times. Okay. So the first L goes along with position A. The second L goes along with position B. So let's roll through this here. Hey, Lorena, in looking at this problem, do you have any fear of potentially being harmed by springs at A? Because that car is like, yeah, that car is like smashed up against a spring, and that's scary. You are right to be afraid. How afraid are you? How many blocks should we put here? And so this is this. I got ahead of myself, and I forgot to talk about that video that we watched the other day with the dead white guy. And the analogy that he used for conservation of injury was a child with some blocks to play with. Okay, and they're always 28 blocks. And the mom always counts the blocks every night. Okay, because Netflix hadn't been invented yet. So counts the blocks, finds 26, goes over, checks the sink. Water level's a little bit higher. Okay, reaches around in the water, sure enough, there's blocks in there. A little while later, counts 20. Can't find them anywhere else, but notices that the treasure chest or the toy chest is a little bit heavier, okay, by an amount equal to 6 blocks. So always able to find the blocks, even if they can't be seen directly, ways of establishing their presence through other means. Except there were some days where she went in there and the water level was at its lowest, the toy box was at its lightest, but there were still only 16 blocks. Why? Because window was open, and some of the blocks got thrown out the window, okay, at some birds or woodland creatures. Comes in another day, finds 32 blocks. What's up with that? Can't get blocks out of nothing. Oh, it's because the neighbor kid, Timmy, came over and brought some blocks with him. So the room is the circle. The room is like the system. We have to be mindful of blocks moving into and out of the system. But as long as the windows are nailed shut and the door's locked from the outside, this kid isn't going anywhere. All right. That being said, Lorena, how many blocks of elastic injury seems reasonable?
3, 4.
4. Okay, cool. So I'm going to draw 4 blocks on that stack. 4 blocks of elastic injury here. Emma, at position A, when the card is at rest, are you concerned about it running you over? No, it's not moving. So I'm going to put an X for EK because we thought about it. Not really scared of it there. Angela, are you worried about it falling on you at position A? No, because it's on the tracks, on the ground, right? So I'm not going to worry about that there, okay? So at position A, all the potential for injury is the spring, okay? So then we look at position B, okay? Mara, at position B, are you concerned about a spring anymore? Nah, spring is sprung, okay? Yang, are you concerned about the motion of the card at that point? Could it hurt you if it ran into you? Yeah, how do we know that? It's got those stink lines coming off of it. It's moving. How many boxes, sir? I asked the multiple choice here. Yeah, okay, cool. So 2 boxes of EK. All right. Cow, could it hurt you if it fell from that height?
Yeah, probably.
Probably. How bad?
Quite a bit. I'm going to give it like a 4 boxes.
All right, how's that make you feel, friends? Why are you uncomfortable? Yeah, it does. We just said so. So what do we got to do? Take off 2, or we're going to go back to the beginning and add 2. I ain't got time for that, so here we go. All right, so we're going to do this. Oops, not going to do that. We're going to do this. All right, and then you got to write your, okay, now we're happy because 4 equals 4, but we need to write that as a qualitative conservation of injury statement. And so the way that goes is I'm going to say E sub A equals E sub K sub B plus E sub G sub B. Okay? So the injury that we had at position A equals the injury that we have at position B. None of it went in or went out. Okay? And so if you were doing this independently, if you said 5 blocks initially, that's fine as long as you have 5 blocks in the end. Okay? So avoid that to avoid chaos. Repeat problem 1A for a frictionless system that includes the cart, the earth, the track. Cart, earth, and the track. All right. So I'm not concerning myself with the spring. Cole, if there's no spring in my system, am I concerned about the potential for injury due to a spring? So I'm going to put an X there. Okay? Chai, at position A, when it's on the ground, are you concerned about this cart falling on you? No. So I'm going to put an X there. Dorn, when the cart's at rest at position A, are you worried about it running you over? No. All right. Moving on here. Position B, Mattingly, are you worried about this cart running you over at B?
I mean, I'm not at the top. Okay, yeah, whatever. Yes.
Yes. How worried are you?
Pretty worried.
How many blocks of worry?
3, 4, 2.
2. Why 2?
I don't know.
There's 2 in the last one. These have to be comparative. We have exactly as much potential for injury due to the motion of the car here as we did in the previous one. Okay? That's a leading statement there. Hey, Jared, are you worried about this thing falling on you?
Yeah.
How worried? 2.
Jared.
All right. Coming back around, Ben, are you worried about springs at B? Shouldn't be. All right. Colin, you're worried about dissipation, thermal injury at that point? Why not?
That's a baseball player. Yeah. He's not worried about space.
Says frictionless. Oops, I got a little carried away there. Got some lipstick on my teeth. Boop. All right, frictionless. So nope. All right, cool. 4 equals 4, right? Not cool. We got more boxes in the end than we had in the beginning. How'd they get in? Or where did they come from? Came from the spring. So I've got to show the spring bringing some boxes over. I'm going to make a box arrow. 1, 2, 3, 4. Arrow. 4 boxes coming into the system. How did they get there? The spring worked them in. So we're going to call this working. And this is the spring. Spring was working. That's how the potential for injury got in there. So I'm going to call this WS equals EKB plus EGB. Okay? That's what's going on there. All right. Moving on down the page. Use the same system as 1A. So same system as 1A is cart, earth, track, spring. Cart, earth, track, spring. All right. But assume that there is friction between the cart and the track. All right. Braden, you worried about it running you over at position A? No, it's not moving. Okay. Francis, you worried about it falling on you at position A? No, it's on the ground. Okay. Madeline, you worried about the potential for getting hurt by a spring at A? You should be. Springs are damn dangerous. How worried are you? 4 boxes. All right. Cool. Moving on to position B. Jules, are you worried about it running you over at B? How worried are you? 2 blocks. All right. Jake, you worried about it falling on you from B? How worried? 1 block. Okay. Michael, are you worried about springs at B? Nope. Springs have sprung. What? Why was what 1? Why was it 1?
There's friction.
So now B is not as high as it used to be? Is the top of the loop lower because there's friction? No, that's still position B. It's the same height. So we've got to have the same EG there. There's friction. What does that imply might be different? If you did the same thing but with more friction, less speed. So what does that make you think? Yeah, a little less EK. What do we want to have for EK? 1. All right. Koba. There's friction. Is there any E-dis involved here? 1 box. So again, I got 4 equals 4. I've got EEA equals EKB plus EGB plus E-dis. Okay? So that's kind of how this thing runs. We're just trying to get in the habit of spotting the potential sources of injury here. Okay, this is all about like first child parenting. How many of you are first children? Okay, very sheltered lives. Your parents were afraid of everything once you were born. How many of you are middle children? No middle children. Middle children don't take AP for some reason. All right. How many of you are the babies? The youngest, okay? No rules for you. Like everything had been, your parents could give no hoots, okay? You were allowed to climb on top of the tallest play structures, go sledding down the stairs, all that stuff. So, but yeah, so we have to be like parents of firstborn children here and look out for all the potential sources of injury. That's what I'm going for, okay? So part D, same as problem 1A, except the final position of the card is lower on the track, okay? So you kind of know how this is going to go. It's going to start out the same. So no EK, no EG, 4 boxes of EE. System is cart, track, earth, spring. EK, yep. EG, yep. EE, nope. Same as problem 1A, so no E-dis, no friction. All right, so this new position B is lower. That means the EG is lower. That means the EK must be higher. It must be faster at that position than it is at the other one. Let me show you one other little tip here quick. Let's say we didn't want 3 blocks there. Let's say we wanted 2.5. Don't do like a stubby, like your pinky toe toenail. That's gross. Okay? People might just think you suck at drawing blocks. Okay? People might try to lick those blocks too, but what you're going to need to do is if you're making a half box, make a triangle like that. Okay? So now that's 2.5 and that's 1.5 and that's 4 equals 4. And so I say EEA equals EKB plus EGB, done. Okay? All right. So there's like 11-ish left. There's 3-ish in your group, so kind of divide and conquer there. And work on that a little bit. 5th hour, 42, you got like 15-ish minutes.
I can do
Get after it.
if you want to do these.